Hi, my name is Christopher Denniston, and I'm presenting our paper on informative path planning to estimate quantiles for environmental analysis. This is done by members of our lab at the University of Southern California. We are motivated by scientific monitoring of harmful algae bloom growth in lakes. In order to study natural phenomena in the environment, such as algae growth, biologists collect physical specimens from the environment to analyze in a lab. However, this is a costly manual process in terms of time, labor, and lab resources, so only a small number of these specimens can be collected. Traditionally, scientists use heuristics to determine where to collect specimens from, based on knowledge about typical growth, wind, and water currents, etc. Our work aims to use an adaptive robot survey to directly suggest collection locations given the spread of the concentration that the scientists are interested in. To do this in an interpretable and flexible manner, our system simply requires scientists to specify an arbitrary set of quantiles of interest, for example, deciles or upper extrema. Spread or deciles could be used for a general understanding of concentrations. High quantiles could indicate dangerous conditions or the worst case, and mid quantiles could indicate typical conditions. Our approach takes high-level interpretable scientific goals as input in the form of a set of quantiles. It helps automate the selection of physical locations, which is a challenging task that has historically depended on heuristics. It also uses robot resources intelligently by tailoring the robot's exploration to the particular set of quantiles of interest, while avoiding exploring regions that do not contribute to the goal. Here is an overview of the problem in our system. There are two main phases that we focus on, which are shown in blue. First, the planning phase when the robot explores the environment. The second is location selection, when the robot uses the survey to propose locations in the environment that the scientists should collect specimens at. First, the parameters for the robotic survey are chosen, such as the bounds of the area and the quantiles for the specimen collection. The robot performs informative path planning, creating an environmental model and an estimate of the quantile value. To model the distribution of interest, we use a Gaussian process that is updated at each step. To solve the planning problem during exploration, we use a partially observable markov decision process formulation, or POMDP, which we solve with a rollout-based solver. Then, once the survey completes, the quantile locations are selected which correspond with the estimated quantile values. To propose these locations, we use a gradient-free, non-convex solver, such as the cross-entropy method. After the quantile locations are chosen, humans can go collect the field specimens, which they later analyze in a laboratory setting. We have four main contributions. First, we develop a planner with a custom objective function to adaptively increase the accuracy of the estimated quantiles as the robot explores the environment. We propose a general loss function for selecting spatial locations which have the values for estimated quantiles. We quantitatively evaluate our methods with diverse sensors on previously collected datasets from real aquatic environments. Finally, we demonstrate our method on a real-world crop health task. In this work, we use a POMDP formulation during planning and exploration. We use a Gaussian process as the model of the environment, which we update with each measurement that the robot takes. The GP model of the environment updates with each new measurement. Locations that have been visited have low uncertainty, represented by the standard deviation as shown in the bottom image. Given the GP model and the objective function, the POMCP planner determines the best next action to take by exploring hypothetical measurements and rollouts from the current state. After taking that action, the robot's model is updated and the process repeats until the available planning horizon is reached. We tailor the objective functions to specifically improve the estimate of the quantiles of interest, rather than the entire concentration which might not be of interest. We propose two new novel objective functions, both taking the form shown here. Delta is defined by the objective, while the added term is an exploration bonus inspired by entropy to encourage diverse exploration of the environment. The first objective function, called quantile change, directly considers the impact of a potential measurement on the current estimate of the quantiles. If the estimated quantile values change, then the action that produces that measurement is more likely to be chosen. The second objective function, called quantile standard error, is similar. It looks at the change in the standard error of the quantile estimates, value actions that change it. This visualization shows concentration value on the y-axis and measured values sorted on the x-axis. The colored lines show the estimate of different quantiles given the values, and the bars show the standard error of the measurements. As more measurements are taken, the accuracy of the quantile estimates increases, as shown by shorter lines, and the uncertainty in those estimates decreases, as you can see with narrow bars around the lines. The second phase of the approach is location selection. After the exploration survey is complete, the robot has a model of the environment and estimated quantile values. The goal is then to select the locations whose values are closest to the estimated quantile values of interest. To this end, we propose the following loss function, which we minimize for location selection. The first term seeks to minimize the differences between estimated quantile value and the estimated value of the location, while the second term introduces a penalty for seeking locations where the model uncertainty is high. The result is a set of physical locations whose value correspond to the quantiles of interest specified by the scientists. In our experiments, we use real data collected previously from natural environments. The first task uses hyperspectral imagery collected from a lake with heavy algae concentration. The second task uses chlorophyll sensor data collected from a reservoir using an autonomous underwater vehicle. We seed the Gaussian process model with very coarse, evenly distributed prior data. This represents something like a satellite image as prior info. We measure the error in quantile estimation during the planning phase. Here, lower is better. The y-axis shows the root mean squared error, and the bars represent different objective functions used during planning. The top shows results from the drone, and the bottom is from the underwater robot. We compared entropy and for the extrema quantiles expected improvement. We find that our proposed objective functions, shown here in orange and green, outperform the baseline methods in the drone and underwater tasks in simulation, and especially perform well when using a camera sensor with the drone. We find that overall, quantile standard error has a 10% mean reduction in median error across all environments when compared to using entropy as the objective function. To evaluate the location selection phase, we measure the error between actual values of the suggested locations and the actual quantile values. The figure on top shows results from our drone experiments. All optimization methods use a proposed loss function except the best visited baseline. Best visited is restricted to choose from locations the robot was able to measure at. Below, the black lines show the contours of the model quantile values, and the stars show the selected physical locations. The background is the error between the ground truth and robot models. To the right, the same selected physical locations are shown, alongside the locations that the robot visited, shown as red crosses. In our field trial, we demonstrate our method in a grassy field, where the robot takes 20 images at a height of 3 meters. On the top right is a visualization of how the drone senses a selection of the field at each point in its path. On the left, you can see the results of steps produced by our planning algorithm, shown as black crosses. And the suggested physical sampling locations, shown as colored stars, where taking crop health measurements are shown. We have proposed an approach for flexible and interpretable analysis for natural environments using adaptive robotic surveys in tandem with the location selection algorithm. Our approach is an important step towards assisting scientists to characterize and study natural phenomena. Thank you for listening. I'd be happy to take questions now.